Okay, so let me back up like 5 minutes from last lecture. Basically, we established a bound for any limit point of the EM algorithm, which I called theta star. So that's any subsequential limit of the algorithm. Okay, so we never proved it converged. It doesn't in general, but you can look at you could look at subsequences of the sequence of estimates from EM. Take a subsequential limit and call it theta star. And then you could look at comparison of this log likelihood that we're interested in. We'd like to maximize. And this function here, which is a penalized guy, you know, and basically, yeah, we end up with this bound everywhere for any subsequential limit. And these two guys meet right there. And proving this didn't require much of anything. You know, basically, all it required was continuity of this log likelihood. And I do stand by my statement that this is like really should have been maybe statement 1 in the book. But then I made a mistake last lecture. I said you can get more from this. And I realized after lecture, not really. Because, yeah, unfortunately, things go the wrong direction. You've got, I don't know, you've got this function here, which like if you linearize this, relative entropy is convex. This might look locally convex. I don't know about this. You might be in a situation where the upper bounding thing is convex locally, and this is concave. It doesn't tell you anything more. You know, it could be, you know, this could end up being a local minimum instead of a local maximum. If you're lucky enough that it's locally concave, then you'd know you have a local maximum. But it all depends. You'd have to know a lot about this to be able to say, am I a saddle point, a local max, a local min, whatever. All right. But just don't forget, this is just a limit point. It doesn't converge, and the ML thing could be over here, and you know it might not work. All right. So it's just that's what makes sure you know that. All right. But it's used a lot in practice, and people have great success. So just like, I mean, it's nothing worse than neural networks, all right? And yet, it's been amazing how successful it's been. You know, in terms of the potential for, you know, local minima and all sorts of issues. Even though it's a non-convex problem, neural networks, backpropagation works in practice. And so and EM is much more, has a much better theory than anything for neural networks. All right, so then we went and looked at applications to hidden Markov models, which gives you Baum-Welsh. Okay, so the setup is just as for EM. We've got some observations Y that were given, and we want to try to fit a Markov chain model, which means we're really trying to find A and B, state transition matrix, and that's a capital B, and the observation matrix. And forget the prior. Let's assume that's given. And again, what's really fun about this is there might not be any reality, right? This could just be data from Wall Street or from a power grid, and there might be no physics whatsoever. We're just trying to come up with a model that fits the data, right? In the homework that we're trying to get finished and send to you, there will be structure. So you're going to apply Baum-Welsh, and you will have set it up so that there's meaning when you finally fit the model. It'll be, by the way, don't worry, it won't be due next week. The official date for the final is on Wednesday, 2 weeks from now, and we'll choose that for the due date for the homework. Okay. So you won't, so you have lots of time to do the homework. It won't be too painful. All right. So we basically, again, let's go through, let's do it again. So several of you, half of you were puzzled by the E step. Let's just do it again, because it is easy. Okay, so for the E step, you have to look at the complete data. And again, the starting point of the nonlinear filter was to express this as a giant product. So it's a product. K equals 1 to t minus 1 of a of zk to zk plus 1, and then for each zk we have the observation. And I guess actually it's too ugly to write it that way. I'll make it prettier. Remember last time I got into trouble with K. K was iteration K in the algorithm. So I'll try to be more careful this time. And what am I missing here, everybody? I missed something. Thank you. Okay, so we've used pi instead of pz1. Pi is not the invariant distribution here. It's just following the notes. Okay, so basically, this is the beauty of Markov models. So you can just write things down in this product form. All right. All right. So the log is a sum. And yeah. All right, so let's go and try to do this. So there's code in there, which let's now expand out. All right. So I take the log of both sides. These are just scalars. Those are just scalars. I end up with a sum of logs. All right. Okay, so this is where we at. I've got the log da 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 da. So we take our kth model, and we take this thing here, which this is a function of sequences. We stick in, a random variables here. This is now true for any sequence. We're going to stick in the random variables. That's why it's capital letters now, and this is now on a computer. We integrate or use MCMC to compute this expectation with a conditional distribution and with the kth model, and then that gives us a function of theta, because this is a theta here. A and B, pi we can ignore. A and B form theta. Yeah. And we go and we write it down. And so let's do it again. So let's take out this boring term first. We have the term I'm going to ignore. Okay, cool. So, so here's where we get into a little bit of trouble because we didn't cover this, how you compute these conditional expectations, all right? So this is what I was saying before. We needed this notation. I'm putting T there, I'll put T there. Okay. All right, so the T's correspond to J there, and the T corresponds to I there. So that was notation we had to put in. So again, you have to go get a script, or write your own code to compute these things. We did not do this. Except, of course, you could marginalize. I mean, you can compute the whole monster smoothing problem and then marginalize, sum out over all the entries, but the T and T plus 1, you'll get this. That's a very inefficient way to do it. So see the book. All right, and so then you can just go and take all these terms out and deal with them. So for example, let's just take one, let's not expand every single term out. Let's just take one. Oh, actually, hold on a second, that's not true. No. Oh, I do need to break it up. Yeah, it's just too young. How do I want to say this? Yeah. Nah, I got to do it. Remember last time I was saying, let me finish it off so I don't have to write this down again. But I really need to. So the first time I'll ignore, because we're ignoring it. And then this here, I'm going to have a double sum, a triple sum. How about S and R? You run out of symbols very, very quickly when you do this. I think I've got it. And there's a log missing, yeah. Okay, so when I want to compute this expectation given y, this capital Y is this little y, and I'm just left with needing the conditional distribution of zi given all the observations of y from 1 to t. You know, so I'm given all the information of an entire time horizon. So that thing is fixed as little yi, it's been observed, and I've just got that thing there, and that's why I have this sum over r of the probability of seeing r right there. That guy is just that. Okay, so you guys had more coffee this time. You look more awake. Oh, that's right. This was the end of a long lecture last time. Okay. So now, what are we going to do? Let's stare at this for a bit. I want to rewrite this. How do I want to say this? Okay. Okay, so now we've got this problem. I want to try to we can now maximize this, and it looks entirely separable, you know, except for the fact, as I was saying, we've got constraints on these guys. The sum of these guys has to be 1. So we've got, luckily the positivity constraints we get for free. The logarithm there means that we don't have to say there's a constraint that it's positive. That's for free. But we do have to know that the sum of our s is 1. And we have a constraint here, the sum over y is 1 for each. The sum over y is 1. Okay. But after that you can see, for all r. Right. So that's that. So each r, that's the probability of an observation, and this is a transition from r to s. So that's what I'm summing here over s and here over y. All right. And the question is, you've got some weird dot products. So for each r, I can take this out and do a maximization of that particular term. So one maximum we have to, for each r, I said, oh God, I did it twice. I was so careful to keep this so it would be consistent. Okay, but so for each r, I have an optimization problem with this constraint. So I won't repeat it here. So here this separates. Because of the way these constraints separate, for each r I have a constraint for this guy when I'm maximizing. For each r I have a constraint on this guy when I'm maximizing. I can separate it into, for each r I get a maximization problem here, for each r I get a maximization problem here. And so what's special here is this AR dot is nothing but maximizing over probability measures, or probability mass functions. So, what can I kill? I can kill those. So you're absolutely right. We could just do calculus, but we want to introduce relative entropy in everything we do. So we're not going to use calculus. So the question comes down to a simple lemma. You see, when you see things like this, we just have so this is given, that's the variable. So basically we just have a dot product here. So the question is, in general, not an RN. So to stare at it like this and just think about whether this sort of looks familiar, it looks like some sort of a entropy-like thing, and so maybe you can manipulate this to something that looks more familiar, and so basically, here's a lovely lemma for you. It turns out the optimizer is aligned with C. So it's just C, but normalized to be a probability mass function. Okay. And how do you do that? So let's introduce some notation to make this more compact. So so let's go through doing this. All right. Let's change. Let's not call it P star yet because we don't know yet whether it's optimal. Neil, I'm thinking of you when I say this. So Neil and I had a discussion recently where we were going through a proof, and the notation at the top made it look like we were assuming we were trying to prove. And so notation can be really confusing. So let's not call it P star yet. Let's call this ratio Q, which is a probability mass function, and let's prove it's optimal. And how do we do that? So I have to look back and think, 'cause it's so pretty, but yeah. But let's go through and do this. Okay, so this division by the sum of the CIs is just a scaling factor. It doesn't change the optimization problem. You know, if I divide by the absolute value of C, I mean the L1 norm of C, you all agree that doesn't change a thing, right? Okay. Okay, so you give me any P, I write down this thing that I'm interested in, and you know this Q is just that, so it's exactly what we're talking about. Doesn't make any difference. What am I going to do? I said I love relative entropy. Looks like I should divide by Q to make it look like relative entropy. But when I do that, I've introduced a Q minus log Q, like an entropy term, so I've got to get rid of that. All right, so I'm done, right? And so remember what this is. I mean, this is equal to a summation over I of Qi times the log, excuse me. I'm going to stick a minus sign in there because everything's backwards there. I want that to be Q over P. And this is minus the entropy. Okay. So this is minus what? And then minus what? Thank you. And you guys were shy here. Thank you. Cool. QED? Okay. So relative entropy is non-negative, and so that's less than or equal to, well, it's strictly less than or equal to minus h of q. Okay, so it's fairly long-winded, but you know, it's just sweet. So this happens all the time. I mean, the reason people use relative entropy as a performance metric in control is because it's so easy to optimize and work with things. You know, I mean, you know, I had this ugly optimization problem, and you could just write it as relative entropy, and you're done. You know, so I mean, I think every student I've worked with almost has played around with these tricks in their research. So we're done then, right? Because we know we can unravel this thing. And could somebody tell me what the answer is? Yeah. Okay. So we're trying to maximize this thing. The maximum, you know, we proved that Q is the maximizer. So what is A star? What is AK plus 1? So basically you've got to swap the sum here, you know, because you've got to put it in there. What is C in this thing? So you've got to do pattern recognition. P is going to be, PI is going to be AR to I. As I said, we're fixing R and then going ahead. And what's CI? I've got an S and an S here, then I've got a big mess. So it's everything else. So I ignore this sum, and I sum over J, and it's just that crazy thing there. So it's a sum of J equals 1 to T minus 1 of just that. Is that it? Yeah, that's it. Okay. And so then you've got the answer. A star from R to I is just equal to C over its magnitude, L1 norm. And then stare at that for a minute. What is that? Can somebody work that out? What happens when you take this and sum over I? T minus 1, isn't it? Yeah. Because you see, if I take this term and sum over I, this was a conditional transition matrix. Conditional transition matrix. This is the probability of hopping from R to I in one step. So if you sum over I, you get 1. That's it. So can you imagine anything more intuitive? I mean, if you were asked to solve this problem, you would, given enough time, you would have come up with a solution. You would have come up with the conditional probabilities of transitions, and then average them. And then that would have been your answer. I think any idiot would have come up with this solution, given enough time. I'm just talking about being locked in a room. You can't leave till you come up with a logical answer. You would get probabilities of transitions for each time j, and then average those, and that's the answer. So it's incredibly intuitive. And the same thing for B. I mean, B is sitting in our faces. All right, so here again, R is fixed, and we just want to maximize over this, and you can see it's the same old object. We've got we're going to max over BR to dot of the sum I equals 1 to T of this gamma R of I times the log and so you can go through and do pattern recognition again. You have exactly as before. Now P is the B instead of the A. It's right there. Well, I shouldn't call it I anymore because there's an I sitting there. I'll call it PL. Okay, that's our P. And our CL again, just to avoid i's, is so that's, yeah, BR to I, and then the thing we're dotting it with, hold on a second. No, I mean, yeah, no, it's trickier here now, isn't it? No, this is not as easy. Yeah. What are we going to do now? Yeah. No. That's what's really important here, is that the way the constraints separate allows us to do an optimization. For each R, we do 2 optimization problems because the constraints aren't coupled in any way. Yeah. So this is true, but it's